Hi guys. In this video I will go over the functional groups that are commonly found in organic molecules, organic compounds. We can begin with the hydrocarbons, which are shown in this table here. Labeled as table 3.1. This is not from the Klein textbook. Many times I'll give handouts from other textbooks. This one is from the Smith textbook, which was used here at AU a while back. The first example of a hydrocarbon would be a simple alkane. These are so simple it's almost not a functional group. Alkane is almost considered just the backbone of a compound, the CH skeleton. General structure shown here, very simplistic. An example shown here of ethane, a 2-carbon alkane. We might show that out full structure. If we did, we would have 2 carbons bonded and 3 H's on each carbon. Each carbon has 4 bonds, no lone pairs. This is sort of condensed, partially condensed. But what we see here is a saturated alkane. And I say saturated because there's no double bonds, there's no pi bonds or rings. And once we cover DUS, you'll know what saturated means. So we can say that alkanes are saturated. The next hydrocarbon would be an alkene. Now with the ene ending, that indicates a carbon-carbon double bond. I don't really know the difference between a general structure and an example in this table, so I'm going to go straight here. But you see the carbon-carbon double bond, and of course to have an alkene you have to have 2 carbons. Where an alkane you could actually only have 1 carbon. For example, methane is a 1-carbon alkane. But you can't have a 1-carbon alkene because you have to have 2 carbons to have the carbon-carbon double bond. This is the simplest alkene, and it is not saturated. None of these here are saturated. These would be called unsaturated. Again, we'll cover that when we look at DUS. And so it's pretty simple. Carbon-carbon double bond there. The next example would be an alkyne. This is your carbon-carbon triple bond. So the ane, ene, and ine endings denote basically single bond, double bond, triple bond between carbons. Also shown in this table of hydrocarbons is an aromatic compound, and the most common example of that is a benzene ring. Again, I'm not sure why they chose to show it twice here, but it is just carbon and hydrogen. The benzene ring is the most common example of an aromatic ring. Definition of an aromatic ring I give you here. That is, all atoms in the ring have a p orbital. Now that's a beginning definition. We will have to expand upon that as we move along, especially in Organic 2 where aromaticity is covered. But for now, that's a good definition for you to start working with. And so every carbon in this ring has a p orbital, and once we cover hybridization, you should hopefully see that. Now, benzene is sometimes called a phenyl group, particularly when it's a substituent. So phenyl and benzene ring is sort of synonyms, same thing there. There are many other types of aromatic compounds. Many of them contain heteroatoms, that is a heavy atom other than carbon. Of course, once you bring in a heavy atom such as nitrogen, it would no longer be considered a hydrocarbon, because hydrocarbons only contain hydrogen and carbon. Now there are other aromatic rings that are hydrocarbons. Those are more unique. The benzene is the most common aromatic hydrocarbon. Okay, in the next table we will see compounds that contain basically heavy atoms other than carbon, and this textbook chose to use a Z to denote that. That's kind of a rare. There's no Z on the periodic table, that's why a Z is sometimes used as a generic, or an X. Typically though, when you see X, it typically refers to halogen, which is actually shown here, X group. So Z is more generic. Okay, an alkyl halide is where you have a halogen bonded to an alkyl group. An alkyl is sort of short for alkane. An alkane halide but when the alkane is more of a sort of a precursor or an adjective, we change it to alkyl. So an alkyl halide is when you have a halogen bonded to an alkane group. A simple example would be a bromine bonded to a CH3. Now the YL ending also sort of indicates it's a so-called radical. The CH3 sort of group, there has to be one other bond here. Of course this is condensed. CH3, and then there's something else there. Now if it's CH4, it would be called methane. But the CH3 group, where you've removed one H and it's just CH3, this is called a methyl, like an alkyl or methyl, but we typically pronounce it methyl. So this would be a methyl bonded to a bromine. That's an example of an alkyl halide. Next compound is an alcohol. The alcohol has an alkyl group and then the OH group, like the methyl OH. The OH group is also known as a hydroxy group or hydroxyl with an L on the end. Now you would not call it a hydroxide because hydroxide, the "ide" ending indicates it is an anion. So that's hydroxide. When it's a substituent bonded to another group, it's called either a hydroxy or hydroxyl. The next is an ether. An ether is an R group, which by the way is a generic for alkyl. There's no R on the periodic table. And the R group can be one carbon, as in this example here, or it could be 5, 6, 20 carbons. When you have a carbon group bonded to an oxygen and then another carbon group on the other side, that is an oxygen with two carbon groups, this is known as an ether. The most simple example would be the oxygen bonded to two methyl groups. When we learn ether nomenclature, we'll call this dimethyl ether. Now, by the way, if you have an oxygen with two ethyl groups, and I drew that line bond, and I drew the oxygen with 2 bonds, 2 lone pairs, standard bonding. That is called, where here the R groups are ethyl groups. This is known as diethyl ether. And diethyl ether was used during the Civil War as a anesthetic. But it's no longer used for that purpose. Today it's mainly used as a solvent in the laboratory. Very flammable solvent. Okay, the OH group is known as a hydroxyl group. The OR group is known as alkoxy group. That comes from replacing the H of hydroxy with alk, which indicates the alkyl group. So it's an alkyl oxygen. If we go this way, alkyl oxygen group, alkoxy. Now, you don't often hear alkoxyl, so I'm not going to say that. Typically, you don't add the L. Alkoxy is most commonly said. Now, what if it was an OR group and the oxygen was minus something very different? Because there's no other bond here. This is actually known as an alkox... what? Alkoxide. Alkoxide. Okay, the next group on the functional group list here is amines. An amine is where you have an R group bonded to a nitrogen. Now, with alcohols, you had oxygen bonded to one R group. If the oxygen was bonded to 2 R groups, it became an ether, a different functional group. With nitrogens, that's not the case. If you start adding additional alkyl groups, for example, let's put by the way, when I draw CH3 groups, I like to actually connect the carbon to the nitrogen, like this. See up here, it looks like the oxygen is bonded to the H. Well, that's actually not correct. The oxygen is bonded to the carbon, and then the H's, the 3 H's are on carbon. So you'll actually see me do it like this most often. Then we can add the 3rd bond. Let's make that an H, and then the lone pair. 2 R groups, but it's still an amine. This is a primary amine, and this is a secondary amine. The primary indicates the number of carbons bonded to the nitrogen. 1 carbon, primary. 2 carbons, secondary. We could also have 3, and I'll just make generic R groups. And that would be a tertiary amine. So the name of the functional group does not change as we add more R groups, but we distinguish the different amines by the primary, secondary, and tertiary terminology. Now, once you start putting 2 or 3 R groups, they do not have to be the same. That could be a methyl and an ethyl, or a methyl and a butyl. It doesn't matter. It would still be secondary. And your tertiary amines, all 3 could be the same, or all 3 could be different. Okay, the NH2 group is known as an amino group. And before we move on to the next one, just show notice the condensed structures. The NR3 condensed here, drawn more fully here. A more complete Lewis structure. Of course, I am using a generic R for the alkyl group. Okay, next functional group, thiols. The thiol is actually analogous to an alcohol. Oxygen with 1 R group, Sulfur with one R group is the thiol. Of course, sulfur is right below oxygen in the periodic table. I reckon this is a generic structure, and this is a precise example where they're using a methyl group as the R group. Of course, it could be ethyl, propyl, butyl, etc. The SH group is known as a mercapto group, or sometimes you just call it a thiol group. And actually, sometimes instead of saying thiol, you may sometimes hear it called a mercaptan. Okay, what if the sulfur has two R groups? Well, that's analogous to an ether, an oxygen with two R groups. In the case of a sulfur with two R groups, it's called a sulfide. This actually is called dimethyl sulfide, where that up there was called dimethyl ether. The SR group is called an alkyl thio group, although you will rarely hear that term used. Just sulfur compounds are much less common, although when you get to biochemistry you'll see a lot of sulfur compounds. I just rarely hear this term. The thiol group or mercaptan group or mercapto group you hear occasionally. Now, just for some extra free information, if sometimes when you get to biochemistry, you'll see two sulfurs bonded together, and then maybe a R group's there. And this is actually called a disulfide. Of course, each sulfur has 2 bonds, 2 lone pairs, disulfide. By the way, if we do analogous oxygen, I'll make these CH3 groups. That's not an ether. Does anybody know the name of that? If you have 2 oxygens bonded together. Now these could actually be H's as well, but this is a peroxide. Now I already see a discrepancy in what I told you, and there are so many discrepancies in terminology in organic chemistry. That's unfortunate for beginning students, but I told you the "-ide" ending indicated anion. Well, actually, these are "-ide" endings that are not anions. Okay. Anyway, these are free. This is free information. These will not be on any quiz or test. Okay, this next table are functional groups that contain a carbonyl group, C double bond O. Now the carbonyl group is not a precise functional group, even though for some reason this book chose to sort of show that under functional group. Not for me it's not, and not for many organic instructors. Carbonyl is a part of a variety of functional groups. It is itself not a functional group. It's too generic. Okay. The first functional group is an aldehyde. That's where you have the carbonyl, and you have an alkyl group on one side and an H on the other. And so, of course, the carbon is making 4 bonds, and the oxygen, of course, is making 2 bonds, 2 lone pairs. Standard bonding all the way around. H is making 1 bond. It's got a duet. So, standard bonding. Example given here where our group is a methyl group. That is an aldehyde. Now if you have R groups on both sides, that is a ketone. And we see examples here. And this is actually acetone molecule there, which you use for washing your glassware in the lab. Now that's a common name. In Organic 2, you'll learn how to name ketones in a more official IUPAC name. Next is a carboxylic acid. That's where you have a carbonyl with an R group on one side and an OH group on the other. And this is a simple example of a carboxylic acid. That is actually acetic acid. Another common name. But these are actually very common compounds that you'll come across in your textbook or the lab, etc. And so they're worth knowing. You probably should have seen acetic acid in Gen Chem, I would imagine. And the anion of acetic acid is called acetate. Next, R group on one side and OR on the other, not OH, but OR, that is an ester. And this is a simple example of an ester. These are often referred to based on the R group here. The name includes this R group, and so since that R group there is a methyl, this compound is a methyl ester. It doesn't matter that this is a methyl. That could be 10 carbons. If that's O-methyl here, it's considered a methyl ester. Little free information, but that's very common and worth starting to know at this point. By the way, we didn't point out over here the R and then the remainder, that is a carboxy group or carboxyl. Okay? If we can make this more generic, this over here is R and then the group. It can be condensed. When you condense it down, you RCOOH or RCO2H. Same thing. Instead of OO, O2. So you can add it over here if you like. I'm just writing it over here. Two ways to condense the carboxyl functional group. Same thing with the ester. This would be a COOR, or you could do CO2R. Of course, there's something coming off. Sometimes I like to indicate with a squiggly line. Something's got to be here for the fourth bond to carbon. In this case, a methyl, or generically an R group. Okay, if the carbonyl has R group on one side and nitrogen on the other side, that is known as an amide. Or as we said in class, some say amide or some say amide. I say amide. The long name is carboxamide. And that's how I usually say that. I reckon you could say carboxamide. That's a little less common. Carboxamide is how it's usually said. When it's shortened, sometimes people say that differently. I say amide. Now, just like amines, primary, secondary, tertiary, with the amide and the nitrogen there, if you start adding R groups to the nitrogen, it still remains an amide. We just switch to the primary, secondary, or tertiary terminology. So this is an example of an amide, but that is a primary amide. Primary indicates that the nitrogen is bonded to one carbon, and that one carbon is the carbonyl carbon. Now if you start replacing these H's with other R groups, you get to secondary or tertiary. Tertiary, you would have 2 R groups instead of 2 H's. Now over here, the amide functional group is condensed. You should sort of see how that is, primary, secondary, or tertiary. Okay, the next here is an acid chloride. This is an R group on one side and a chlorine on the other. Now it's called an acid chloride because it's typically made from a carboxylic acid. Now these all are made from carboxylic acids, but for some reason this sort of became known as the acid chloride as opposed to some alkyl chloride. Now it's also known as an acyl chloride. That may be a more official name because the acyl is actually where you have an R group and then a carbonyl. So just an R group is called an alkyl, and just a CO double bond O is called a carbonyl, But together all that is called an acyl, and then if you tag on a chlorine to that carbon, it would be an acyl chloride. Specific example, and that's condensed down version. Now, you might be wondering, what about an acyl bromide or fluoride, etc.? Those are possible, but they're much less common. With alkyl groups, or alkyl halides, the X group can be F, chlorine, fluorine, chlorine, bromine, or iodine, and they're all fairly common. And the example would just use bromine. By the way, I see I skipped the aryl halide. We'll go back to that. But when you get to acid chlorides or acyl chlorides, chlorine is by far the most common. You rarely will see the other halogens. That's because this is really a reactive intermediate. You're not going to find acid chlorides in nature. They're an intermediate that's made in the lab and then used, and because of that, organic chemists typically just make the acid chloride version. Now back over here, we skip the aryl halides. Aryl halide is when the halide is bonded to an aromatic ring. And aryl denotes that it's sort of a fragment, just like alkyl fragment, and then we have an aromatic aryl fragment. So this is an aryl chloride. You can have aryl bromides, aryl iodides, etc. Of course, that's the benzene ring. When we get to organic 2, we'll learn to call this chlorobenzene. Simple enough. Okay, there's 2 other functional groups that I want you to know that were not on the table from this textbook. I believe these are in the table in the Klein textbook, though. I think these are very important. That's why I want you to know them. Nitrile. This is an R group bonded to a carbon triple bond N, which is called a cyano group. Okay, cyano group. You need to know the full Lewis structure. That's condensed. No bonds or no lone pairs shown. Full structure. And so this is a an example of a compound, a nitrile, that contains the cyano group. That's a 3-carbon. It's actually 4 carbons. The R group portion is 3, but the functional group itself contains another carbon. So if we were to write this like this, well, that's just condensed for this. There's one more carbon other than the R carbons. Next is sulfonamide. This is actually analogous to the carboxamide. So that was R carbonyl nitrogen. This is R sulfone nitrogen, or SO2, which is known as a sulfone. So it's a kind of a sulfonamide, and that's sort of shortened to sulfonamide. So sulfonamides are analogous to carboxamides, but instead of containing the carbonyl, they contain the sulfonyl group. Now, carboxamides are shortened to amides. You do not want to ever shorten a sulfonamide, because if you shorten this to amide, you're referring to the carboxamide. So we always use the long term. But just like regular amides, if we start putting R groups on the nitrogen, we start using the primary, secondary, tertiary terminology. So we have the sulfonamide functional group. Okay, here at the bottom are some examples. Atenolol, a compound, a drug used to treat hypertension. Functional groups, they've been labeled for you. Amide, right? Carbonyl bonded to nitrogen. Plain R group. Carbon group. Aromatic ring, that's a benzene ring, the most common aromatic ring. Yes, every carbon has a p orbital in the ring. Oxygen bonded to 2 carbons. It's an ether. Right? Oxygen bonded to 2 carbon groups. Now, R can be alkyl. R is actually quite generic. Sometimes people will say it's an alkyl group, but it actually can also be an aryl group. See, here I said where R is an aromatic ring. Some people have sort of different definitions of R, but it's quite generic. An OH group bonded to a carbon that looks like an alcohol with the hydroxy group or hydroxyl group. Nitrogen bonded to 2 plain carbons, amine. What type of an amine? That's a secondary amine, yeah? Now be careful. See, it's not bonded to carbonyls. If it was bonded to a carbonyl, it would be an amide. Bonded to plain carbons, non-carbonyls, it's just an amine. Viracept, compound used to treat HIV. We have an amide here. That's a secondary amide. Nitrogen's bonded to 2 carbons. We have an amine. Nitrogen bonded to 3 carbons. Now that nitrogen is part of a 6-membered ring. That's okay. It doesn't matter. It's a nitrogen bonded to 3 carbons. It's a tertiary amine. No carbonyl. It's not bonded to a carbonyl. Alcohol, yeah. Amide. That's a secondary amide. Sulfide. By the way, sulfides can be called thioethers. Didn't say that over here, but thioether. That's because it's analogous to an ether. Oxygen 2R groups, but sort of a The thio term denotes sulfur. Okay, there's two others I want you to know. When the OH group, which looks like an alcohol here, oxygen bonding to one R group, but when it's bonded to an aromatic ring, it actually gets a different name. It's called a phenol, OL. Don't confuse that with YL. Okay. Phenyl is a term for a benzene ring. A phenol is a benzene ring that contains the alcohol group with the OL ending. Like an alcohol has the OL ending. So it's sort of a blend of phenyl alcohol. Phenol. We always want to call that a phenol and not call that a plain alcohol. Also with amines, if the amino group is bonded to an aromatic ring, such as a benzene ring, it's called an aniline. Now it has the INE ending. Not sure where the anyl part comes from, but this is an aniline. And there's no aniline shown in this structure. But I want you to also know that one. So that's a unique type of an amine that goes by this name, and that's a unique type of alcohol that goes by this name. Okay, for practice, you can do problems in the workbook. On page 2. And so when you look at structures, you can now we now have terminology where we can discuss the structure. Just like a human body, you know, you look at a human body and you can say, well, those are hands and there are legs and there are feet, and the human body is made up of different body parts. Well, organic compounds are typically made up of different functional groups, and we need to be able to have terminology to discuss those building blocks, those functional groups. And so what do you see here? What do you see here? By the way, ME group. That is my abbreviation for a methyl group. Many chemists do abbreviate the methyl as a ME. Of course, a methyl is a CH3. And there's also methyls here. So you need to become familiar with different ways to draw structures and terminology used to discuss them. Now, of course, answers to your worksheets are in the back portion of the workbook. There's also some warm-up questions where you can name functional groups on the first page of the handout. Okay, guys, so that was an overview of the functional groups. We'll see what type of questions come up. And we'll go from there.